Hi, I'm Carl Winkler from Experimental Services. Today, I'm going to give an explanation of a fatigue crack growth system that's used for material evaluations. I'm going to talk a little bit about the system, the components that go into it, how to conduct a test, and some of the results that come off of the data we can look at. I'm going to explain a little bit about the fatigue crack growth system components, starting with the load frame. This happens to be a tabletop load frame that has a hydraulic actuator mounted in the crosshead. It happens to be a 5-kip actuator, and as you travel down the load frame you can see the columns, and it's tied into a base, and we have the base tied to a rather substantial inertia reaction base to stop any extraneous vibrations from propagating through the system. Going back up, the actuator itself is what's going to excite the test specimen inside the chamber. And the actuator has an LVDT inside of it, which is actually a instrument for measuring displacement very accurately. So that's how we're going to determine the strain that's put on our fatigue crack growth sample. Around the specimen itself, we have a temperature chamber. This temperature chamber can be controlled very accurately to any temperature we choose to run the test at. Below the temperature chamber, we have some ductwork coming in from a humidity control unit so that we can control humidity and temperature together on the test specimen. Below the chamber, we have a load cell. This reaction load cell is tied into the bottom fixture that we're going to use to grab the specimen, and this actually will measure the load transmitted through the sample during strain input. Inside the chamber, we have a light in the back for backlighting. We have 2 grips, which are going to hold our specimen. The specimen is placed between the 2 grips, locked down, and then behind the grips we have a piece of opaque plastic to provide some contrast between the black specimen and the crack and the background, so that we can get an accurate photograph and calculate crack length very accurately. You can see that inside of the chamber we have a glass partition, of course, in the temperature chamber that we've cut, and that's so that the camera can shoot right through the cut in the glass and get a very clear picture of the crack in the sample. And of course, on the outside we have our digital camera. The digital camera is controlled by our software, which we'll explain in a minute, which is going to be able to focus in on the crack very accurately and take a picture of the crack during testing at specified times, specified cycles, and we'll be able to use that digital image to calculate crack length. Over to the left, the next major component is a closed-loop servo-hydraulic controller. This is actually doing the control of the test inputs to the specimen. The signals are sent over from the computer, and then this does the conditioning of the load cell and LVDT, sends the signals out, looks at the feedback, makes corrections so that we maintain very precise and repeatable controlled input conditions. Further left is our temperature controller, of course, where we can set the set point, and it will do closed loop control on the temperature inside the chamber so we can very accurately condition the sample. To the far right, we have our computer control system, and this happens to be the software package that we've written that's going to take the inputs for the test conditions and send those to the controller and allow the controller to pulse and cycle the sample, and then this will also monitor the loads and the strains and the other pertinent information and perform some calculations for material properties and fatigue crack growth length and things like that that we want to examine during the test. Now I'd like to take a look at the fatigue crack growth sample itself and walk through a little procedure on how we might prepare this sample for testing, install it in the machine, and start a test. This is a typical pure shear sample. As you can see, it's got a relatively long length compared to its height. It's also typically fairly thin, maybe on the order of a millimeter or less. And this sample, the first thing we do to prepare this for fatigue crack growth propagation is we're going to measure it. We're going to have some accurate measurements of thickness along the sample. We have to know its length. And then the next thing we're going to do is we're going to prepare a controlled crack in one end to start the crack for our test. Typically this crack is going to be about an inch long, 25 millimeters long, made with a razor blade. And then when we install it in the test machine, it'll have a place for the crack to start propagating from. So first thing we would do is we'll measure this just with a set of calipers. And we record this in a computer program. So we go along the sample 5 places. And we measure the thickness and type it in. Okay, now we've measured the thickness 5 places across the specimen, and the computer program calculates an average, and now we'll just get an idea of the length of the specimen. And these will be input into our fatigue crack growth propagation program so that we can calculate geometry and figure out what the strain should be and what the modules will be in the material. We have a custom fixture that we use to do this. You can see it's a piece of aluminum that has a slit so that a razor blade can pass through it. And then a lower fixture for holding the specimen. Put the specimen inside the fixture. It helps to wet the razor blade a little bit so it'll cut the sample easily. And we have the pre-cracked specimen. Next, we're going to install the pre-cracked specimen inside of the test fixtures. Open the machine. We work the fixture inside of the grips, and the inside edges of these grips are serrated so that they grab the specimen very tightly and don't allow any slip. We tighten the bottom down first so that it's all the way seated evenly. Tighten the top last. And now our specimen's installed and it's ready for test.